Okay, today we're going to be finding the volume of a 3D surface. First, let's use a Riemann sum to derive the volume. Let's say we have a 3D surface like this. Now, using Riemann sum, like we did in BC, we're going to break it into prisms so that it'll become something like this, where a bunch of little prisms make up the surface. So just like in BC, instead of having two variables, we're going to be doing dA, which comprises of dx, dy. Now, does it matter if it's dy dx or dx dy? No, and this is Fubini's theorem. So using the limit definition for Riemann, we have, if we have the limit of mn goes to infinity of, let's have n, I, and I is each prism, each of these prisms, oops. And then we have the function, which is in x and in y. And this point here is like the CI point, where on the 2D xy, any point in the grid that dx and dy are going smaller into, any point in it is randomly chosen as the CI point, which is xi, yi. And then this with delta x, delta y becomes dA. And then applying the limit onto the sigma notation, which is the Riemann sum, if we take it to infinity, which means the norm will go to infinity, this means that the prisms will become smaller and smaller until they approximate the area. So then it becomes the integral of the region fxy dx dy. And again, it doesn't matter if it's dx dy or dy dx, because this is Fubini's theorem. And then let's practice writing the bounds for a function, like if it's dx dy or dy dx. And this is called vertically and horizontally simple. So if we have take the xy trace of this function to find the region that's here that we're approximating the volume of. So let's say the region that we're approximating for the xy is something like this. If we are doing it horizontally simple, it will be like this. It would be like taking a bunch of slices this way. You can imagine the function sticking out like this and having a varying z value. So it'll be something like this. And then if it's horizontally simple, it'll have dy on the outside and dx on the inside, because you're going to be slicing it like this. And then for each slice, which is dy, for each slice like this, you then go along the x and go dx like this. So for and you then go like dx. And then for vertically simple, it's the opposite. You take each slice like this, so it's like a sheet, and then you go like a sheet like that, and then you approximate the x, and then you go like this. So this is the final Riemann sum that we decided, which becomes the integral. The whiteboard is weird. Okay, which becomes the integral. Oh, there's not y. Oh. Which becomes this integral dx dy. And then to explain this part again, what was the volume, or what is the usual volume equation? Volume is usually base times height, right? And then the base here is the area of the little rectangle, and that's this part, which is dA, or d area. So that's the base, and then the height is just the zth element of that select point in the randomly selected point in the rectangle of the prism, like the prism. Oh. So, and that's this over here. So this is the height, which is f of zi, yi. And then the sum of that becomes approximately, taking the limit of that, limit of that goes to 0, approximately becomes this integral. And then how to evaluate this double integral is to rewrite this as a little derivation is to rewrite this as parentheses, right? So we first evaluate, why is the pen so weird? So we first evaluate this inside portion, and if we evaluate this part, we can write it as taking the limit of this part, limit of m to infinity, j equals j, I, j, of this part, arrow, it becomes integral of from a to b f x I x y j I dx j. So basically this is a function of y, because this integral changes as yi changes, even though the integral is evaluating x. So we can say that g of y is equal to this integral I. And because this is a function of y, then we can then put it back into this original function and say that this sigma, or this summation, becomes c to d g of y dy. Now if we plug this integral back into here, we now can prove that we can evaluate the double integral by first evaluating the inside and then evaluating the outside, because this will give a function of y for a three-variable function. Yeah, so to evaluate double integrals, you first evaluate the inside by holding y constant, and then you get a function based on y, and then you can evaluate the outer function holding x constant. Now, the geometric interpretation of this is interesting because it's similar to the BC concept of taking the volume by making cross sections and having different cross sections. But the difference is that here the cross section is not exactly the same. In BC, it looked like it would be like a pile of rectangles, for example, and every cross section would be the same shape, and it would only depend on x and y, or it would look like a bunch of triangles sticking out. But in Multivar, the z value is varying because it's changing. So then the cross section is a different shape. It can have a different area. So you can't use the same method in BC. So instead, visually, taking two integrals, it will look like, if you have a shape like the one I drew earlier, like this, it will look like first going through each and taking a slice. So if I slice this in with dy, I will get a shape that looks like this. And then over here, I will get a shape that looks like this. So you can see that the two shapes are different. And that's why we need the second, the second integral, which goes the dx direction. So then in this little slice, it will then take a rectangle here and go along the x-axis to find the area of this slice. So then the dx gets, this is the dx dy. The dx gets the gets the area of the slice, and the dy adds up all the slices. If we were to do dy dx on the other hand, it would be similar. It would be like going across the x to get this slice, which is kind of like a rectangle, and then the y, so like this way, taking the rectangles here and adding up to get the area of the slice. So yeah, that's an interesting geometric interpretation. And now we'll go into an example. Now we're going to try an example, which is 27 in the book. You can see the shape here. I also drew it here, but this one's a little better. To demonstrate the concept of horizontally simple and vertically simple, like visually as a 3D interpretation again, taking the slices, if we have dx dy, which is on the 2D xy cross-section, it would look something like, yx cross-section, it would look something like dx dy. So first taking this slice, and then first taking the slices this way, and then summing up each slice this way. So first, like this rectangle, getting these little rectangles, and then taking the sum of the rectangles. So 1, 2, and dx dy is the opposite. Now, if we want to look at how this looks on a 3D level, if it were dx dy, so first we do dy, which is along this axis, dy. So we take the slice like this. So for example, at the very end here at y equals 1, the slice will look like this. So then we have a bunch of slices. And they can vary in shape because the z is varied. So that's the first step. And then the second step is to get the dx, which is this on this axis. So for one slice, we'll have a bunch of rectangles like this. So now let's try to solve it using dx dy. Writing the double integral like we learned earlier. First, we have dx dy, and the function is 1 minus xy. So first, dy is with this bound. So what are the bounds for the y? Looking at the xy trace, which is very helpful to draw the xy trace, we have y goes from 0 to 1. So that would just be 0 to 1. We'll just be taking the slice from 0 to 1, each slice. And then for the x, what are the bounds for that? So we go here to here. So to get this part. So we can see that for the x, it goes from 0 to y. And that's because it goes from, let me draw it a little bigger, it goes from this point to this point, this point to this point. This is what the x goes from, right? Like this, this. And this point here, this is 0, this is 0. This point here is the line y equals x. And since we want the y coordinate, it's given by, since we want the x coordinate, it's given x as a function of y equals to y. So then 0 to x of y, which just equals to y. And that way, evaluating the inner integral also makes it a function of y, so we can evaluate the second integral, which is dy. Now let's try to actually evaluate this. So again, starting with the inner integral, treating y as a constant, evaluating gives x minus x squared y over 2. And then we go from y to 0. And that'll be, plugging y for x is y minus y cubed over 2, and then minus 0. So this is nothing. So it just becomes y minus y cubed over 2. And then we have the outer part of the integral, which is 0 to 1, dy. So integrating this in terms of y, treating x constant, but there's no x, it becomes half y squared minus y to the 4th power over 8. And the bounds are 1, 0. Plugging in 0 will give 0, so it's just plugging in 1 to this equation, which then becomes 1/2 minus 1/8, which is 3/8, and that's our volume. Thank you.